welcome to the seminar. I'm very pleased to introduce the best thing to have happened to psychology.
Thanks, John.
I'd like to think that you all know Andy, so I'll dispense with the usual plotted history. I'm particularly fond of Andy at the moment because not only has he curated and introduced a film in our cinema series, which was about data and the misuses of data, if you like. He's also agreed to give this talk today. This is a slightly different talk to the usual, but this will give us a good introduction, I guess, and a good think piece about open science, reproducibility, and all of these important things that are buzzing around at the moment. So thank you very much, Andy.
Thank you, Ali. Hi there. It's great to see so many people come. Thank you. It's got a mixed audience. Just so you know, I've attempted to pitch this at a relatively introductory and practical level. So there are some people in this audience who know at least as much about this sort of stuff as I do. I apologise to you in advance. This will be in the form of revision, I think, in most cases. To give you a bit of idea of how I'm going to approach this, the argument's basically going to be as follows. It's going to be that one of the most positive things to come out of the replication crisis is an increasing recognition of the importance of doing open, reproducible science. So I'm going to tell you what the replication crisis is, consider what caused it, and show how good open science practices can help us solve those problems. Much of it's going to be pragmatic, a how-to, and I'm going to argue that the replication crisis may have been one of the best things to ever happen to psychology, if it changes the way we do things. Okay, so for those of you who don't know, what's the replication crisis? Well, psychology changed, I think, forever on the 27th of August 2015. For about the previous 4 years, 270 psychologists around the world have been rerunning 100 high-profile published psychology experiments. Some of them were run by people in this school. Now, finally, these 270 psychologists were ready to share their findings. The results were shocking. Less than half of the rerun experiments worked. So here's a table from the paper from 2015 in Science. You can see that whilst there are potentially differences between fields, I don't really want to focus on that because that's not really the main point here. The point is, even if you're feeling smug because you're on the cognitive side of psychology, you shouldn't be, because the best figure here is that cognitive psychology experiments replicate about half the time. That's terrible. Okay, so if you're feeling smug, you shouldn't be. The fact that it's a bit lower elsewhere, you know what, this is the problem. Most of what we do doesn't replicate. Why did that happen? How did we find ourselves in this position? I mean, to be clear, this is not just psychology. I'm talking about psychology because this is a psychology audience. There are similar problems in economics, in cancer studies. This is a broad problem, but we're focusing on psychology today because that's what we do. So why did this happen? How did this happen? Well, I'm going to give you an opinionated summary of why we found ourselves in this position. And because, you know, magic numbers, 3 or 7. 3 didn't seem quite enough, so 7 causes, I think, of the replication crisis. These are not a complete list, and they're not in any particular order, or you should at least infer an order from them. But here are the things I'm going to talk about today. So I'm going to talk about each of these, and then I'm going to suggest practical ways you can solve these problems in your own research. So the problems are publication bias, overly small sample sizes, not understanding the statistics that you're using, low reproducibility, which we'll come to if you're not sure what that means, p-hacking, again a technical term, if you haven't come across it I'll explain it, poor project management skills, and also some problems with our publication norms, the extent to which we expect voluminous publication. So I'm going to go through those in order. So let's start with publication bias. So on the next slide we have something called a funnel plot. Now if you've not come across funnel plots before, these are quite fun, I think. So what we have here is on the x-axis we have the size of an effect in a particular experiment. So you don't need to worry too much about the scale here, but the point is that if a point on this plot is at 0, then there is no effect. So the extent to which the points are skewed to the right of 0 is the extent to which you're seeing an effect in that direction. So that's the x-axis. On the y-axis, you have a measure that is essentially a measure of sample size. It's not quite that actually in this graph, but you can studies with larger samples are going to be towards the top of this axis. So what you'd expect to see is if you have studies which have lots and lots of participants in them, then you'd expect to get quite a good estimate of what the size of the effect is. And so as you go towards the top of a funnel plot, all those points should be roughly where the average of the points are. As you come down the funnel plot, as you have smaller numbers of bits of data, you should see a spread, because small experiments don't estimate the size of the effect very well. Now, if this is working properly, then the funnel plot should be symmetrical. I mean, there are, in fact, as some of you know, reasons why it might legitimately not be symmetrical, and we're not going to go into those today. But normally, you'd expect to see it symmetrical around its midpoint there. I hope you can see that this one really isn't. That there is a big gap. Do we have a pointy thing? There's a big gap here. So we have lots of small studies where the effect is in this direction. This is data that I picked on from cognitive bias modification. This is where you train people's cognitive biases, for example, like attentional bias, and you try and help their anxiety or depression through doing this. You can see that there were quite a few studies with small samples that showed a positive effect. There appear to be no studies that show a negative effect, despite the fact that as you go up, you can see that when you run large studies, the effect is very small and roughly 0. The average of all the points is very close to 0. Probably these were run first, and this is why all these ended up being run as well. The question is, where are these? Okay, they appear to be absent. And normally, the answer is they exist, but they weren't published. So people ran them, they didn't work, they thought, oh well, never mind, sometimes experiments don't work. And that was the end of it. I've picked on cognitive bias modification for various reasons, but it's not unique. If you're interested, I can show you more than 10 graphs like this from different types of psychology, most of them having this gap at the bottom of the funnel plot. So this is a complicated plot to make a really quite simple point, which is significant results are easier to publish. Okay, probably almost whatever stage of your career you're at, you already know this, or at least you know that's the nature of the psychology that we've grown up with. Why is that? Well, at least one reason, I think, is because of people actually correctly interpreting the statistics that they're using. You've been told in statistics class that if you do a traditional test like a t-test, then if you get a p-value less than 0.05, great, you have an effect, you can publish, you know, fantastic. If your p-value is greater than 0.05, the correct interpretation is it's as if you hadn't run the study. Now that's crazy, because it can't be as if you haven't run the study, because you have more data. It's really extraordinarily unlikely that you know more about a phenomenon and yet you know nothing more about it. But that's the craziness of that type of statistical analysis. The one that you've all been taught has this crazy aspect, and you know it, you've been taught it, and most of you remember it, I'm sure. It comes down to null results in traditional tests like a t-test are meaningless. And therefore it's appropriate to not publish because you haven't found anything. This turns out to be incredibly easy to solve. And without getting into the history here, we've known how to solve this problem. We can argue we've known how to solve it since about the 17th century, but in psychology we've known since Jeffrey's work in the early 60s. But it hasn't taken off yet. Main reason it hasn't, I think, is because the sums used to be really hard to do and you had to do them yourself. Now the sums are very easy to do, which we'll come to. So what's the answer? Bayesian statistics. There are Bayesian versions. Doesn't really matter what that means for the purpose of this talk, but there's another way of doing a t-test that gives you a different value, not a p-value, but what's called a Bayes factor. Now, the most important thing about Bayes factors, the one reason you should think about looking into them if you haven't done already, is because they allow you to interpret null results. In particular, if you get a Bayes factor, this is again a convention, you get a Bayes factor of less than 1/3, that is considered to be some evidence that there is no difference for the group, between the two groups. No difference in your experiment. So it's evidence for the null, something you can't get from traditional statistics. Another good thing about the Bayes factor is that it's relatively easy to understand. We'll have another example later, but actually, even if you think you understand p-values, you probably don't, and we'll get to that. Bayes factors are exactly as easy as they look, though. So you have this number. If the number is less than 1, you have some evidence for the absence of a difference. If the number is bigger than 1, you have some evidence for the alternative hypothesis, normally that there is a difference. The further your number is from 1, the better your evidence. And it's an interpretable scale. And like we have a convention of p equals 0.05, we also have a convention that we don't really bother to interpret Bayes factors if they reside between 1/3 and 3. Outside of those, there's something to talk about. And the further outside it is, the more confident we are. Okay, just a little bit more about this, because we're going to use this concept a couple of times. What a Bayes factor actually is. So a Bayes factor is how much you should update your belief. So imagine, for example, you start with a fairly, loose belief that your null hypothesis, the no difference, and the alternative, the presence of a difference, that they're about equally likely before you collected any data. You then collect your data, do a Bayes factor calculation, you get a Bayes factor of 3. Oh, there's a spelling mistake there. After you collected the data, you got your Bayes factor of 3. The way you use that is it's now 3 times as likely that there is a difference than there isn't. So the Bayes factor is a way of updating your belief from a starting point. We call that the prior and the posterior, before and afterwards. One of the reasons that makes Bayes factors very handy is because it allows you to do something that is really not possible to do with traditional statistics, or at least not easily, and we really need to do. So it shouldn't always be the case that your belief before running the experiment is that the null and the alternative are about equally likely. Imagine, for example, you're looking at work on extrasensory perception. Okay, so the idea that I can use telepathy to communicate to Peter what shape I'm thinking of. Probably we don't think it's equally like. I'm not going to try it, don't worry.
Please
Yeah.
do.
Go on, what shape am I thinking of?
Is it a rhombus?
No, it was a dodecahedron. Close though. You knew it wasn't going to be common. Right. So probably we have a very low belief in the alternative, so the presence of ESP. Maybe if we're not trying to be too categorical about it, we might say, well, there's no known physical process, so maybe I think it's about 1,000 times more likely that that ESP doesn't exist than it does. You then see some experiments on ESP where the Bayes factor is actually quite substantial, 10, 40. Well, that means that now, I thought it was 1,000 times more likely there isn't an effect than there is. Now I've collected some data, I've got a Bayes factor of 10. So now I think it's about 100 times more likely there isn't a difference than there is. So the great thing about Bayes factors as well is you can use them to update beliefs from where you are, not just always start from a standard sort of, I don't know, kind of point of view. And the I don't know, ESP is an extreme example, but without getting into a whole nother debate, there are frankly some pretty unlikely hypotheses that we've seen of late in the replication crisis. They often end up in psychological science. And maybe we should be thinking about what the likelihood of this hypothesis was prior to collecting data. That might help. The very easy way of saying this, the aphorism is, extraordinary claims require extraordinary evidence. P-values don't let you do that, or at least not so naturally. Okay, so don't be afraid of Bayes factors. They are no harder to calculate nowadays than a t-test. If you happen to be in the first year of this course, you already know this. It may be that you didn't find t-tests that easy to calculate, but it's no harder than doing a t-test. So, for example, I'm using R because I like R, and also because SPSS has been very slow to the party on Bayesian statistics. This is how you do a Bayesian t-test in R. The first command just loads in a part of R, which allows you to do Bayes calculations. The second command is what you type. So you've got t-test BF, well, I'm doing a Bayes factor t-test. I've got something that is a formula, so it says, okay, I want to look at how sex, that actually means gender here, is related to annual salary, so income. And I'm saying that I want the data is in a data file, well, a data frame actually called CPS data. That's it. You run that command, you get this output, that number there, that's your Bayes factor. So the Bayes factor for the idea there is a gender gap in annual salaries in this sample is about 18. So if you thought that was equally likely to be true or untrue before checking the data, it'd be interesting to see who thought that. Hopefully none of you. This would update your belief. You should now think it's about 18 times more likely that there is a gender difference than before you ran it.
Can I
Yeah.
ask you understand the question? But
Yeah.
So if previous to that, I would have thought that it's 18 times more likely that there is a gender difference.
Yeah.
Would then the Bayes factor come out as 1?
Not as one, because you're taking a ratio, right? So you're taking.
So afterwards, it would be even more likely. So
It
but
still
would be
scales
smaller,
up.
but
Yeah,
it would be smaller.
it still scales, but you're never going to get to infinity, right? Because it's a ratio. But, okay, good. Is that all right? Okay, so easy to do. So what we have publication bias. One of the reasons we have publication bias is because it's hard to publish null results, because null results are meaningless when you use regular statistics. They're meaningful when you use Bayesian statistics, so start using Bayesian statistics. Okay, we've started doing this in our lab about 4 years ago now. We've published a whole bunch of null results, which is good, right? Particularly if you're a PhD student and you want to publish some papers. We'll come to that. Okay. Issue 2. Small sample size. Mostly, we're not collecting enough data. Okay, there's quite a lot of good work on this actually. So, study by Marsalek, looking at mean total sample size in psychology experiments. Median actually, but typical total sample size, about 40 participants. We also know that the median effect size in psychology is about a D of 0.5. So this is done from meta-analysis, so this is from real experiments. It's not just someone going 0.5. This is roughly how big effects are in psychology on average. Not all of you will know what a D or an effect size is. Basically, it's the difference between the two groups in terms of their mean divided by the standard deviation, essentially. So it's how big the difference is compared to the variance. So the things with big effect size are easy to detect for that reason. Now you put those two things together. You put together how many people we typically test and how big effect sizes typically are in psychology, and you can calculate something called a power number. Now a power number is just the likelihood you would find a significant effect if it was there to find. So a power of 80% means if there was a real effect on the population, then on 80% of the occasions, this is simplifying slightly, but it will do, on 80% of the occasions, you would find an effect if it was there to find. The typical power of a psychology experiment, if it's using an independent samples test and it's using a typical sample size and you're looking for a typical effect size, typical power is about 0.35. So for first approximation, given the sample sizes we tend to collect in our subjects, we're more likely to not find it than find it. Some of you have been taught about power. We generally are taught right from the beginning that the minimal standard for data collection is that you should have a power of at least 80%. Yeah? We're way below 80 in much of psychology. Great paper by Bakker. On average, looking at all, surveying people's intentions of what they want to do, and how much data they collect, you need to collect about 3 times as much data as you think you do, approximately. Not all of you, some of you are thinking about it differently, and you'll be right. But on average, psychologists need to collect about 3 times as much data as they actually do to get adequate power. Now, just to make this even worse, this interacts really badly with publication bias. So, most studies are underpowered. And of course, the smaller ones are going to be particularly underpowered. And we only publish the ones that are significant. The ones that we publish, therefore, are the ones that overestimate the sample size. Yeah? You know, but they've just got lucky stroke unlucky, and have got got an effect size that appears much larger than it actually is, which is why it got published. So our estimate of how big effect sizes are in psychology is probably an overestimate, because it's being skewed by the ones that didn't get published because they didn't work. So this is really bad. How do you solve this? It's easy, again. You do a power calculation. Again, other software is available, but this is really easy to do in R. Again, just 2 commands. First one, library power, so it's loading in a piece of software into R that does power calculations. And then the following command is working out the power for a t-test. So power t-test is the command, and then you specify the things that you know, and the computer tells you the thing that you don't know but want to. So for example, I want a power of 80%, so 0.8. I'm expecting an effect size of 0.5. If I don't know what to expect, let's go for that, because that's fairly typical. I'm looking to pursue something at a significance level of 0.05. Power calculations are based on traditional statistics, which is a whole other thing we could get into, but for now, let's not. And we're looking for a 2-sample test, so we're not assuming a difference. You tell R that, and it tells you how many participants you need in each group. Okay, you need about 64 participants in each group to achieve 80% power with a typical effect size and a typical significance level if you don't have a directional hypothesis. That's about 3 times as much as people actually do, because they typically run about 20 participants per condition. If you're doing within subjects designs, it's completely different. Okay, so good for you, those who are. Not all of us, unfortunately, can do within subjects designs. It's quite a lot of learning research. It's quite hard to do within subjects, because you learn something and then it's hard to get them to not learn it. But yeah, where you can, do within subjects designs. And we can get into that. If you're running 40 participants in a single condition, then your power is going to be much better than this. I'm looking at Patrick here. I think most of his work is within subject. Okay. Good. Right, so that's how you calculate it. Relatively straightforward. Okay, good. Right. So we've talked a little bit about power. We talked a little bit about base factors. And so we're going to just continue a bit now, and I'm going to ask you a question. Okay, so you're running an experiment. You anticipate a small effect. Okay, let's say a D of 0.2. So you're going to run a really well-powered experiment. You're going to test 500 participants, which actually is close to what you need to get adequate power with a D of 0.2. It's about 350, I think. But anyway, you're running 500 participants. You do your test and you get a p-value that's between 0.04 and 0.05. Okay, so significant. Just the right side of significant, but significant. There are 2 things that I'm going to ask you to choose between. One of these is more likely than the other. The first one is that the null hypothesis is more likely. It's more likely there is no difference than there is. Other possibility, the experimental hypothesis. Well-powered study, p-value between 0.0 and 0.05, the experimental hypothesis is more likely. It's more likely there is a difference than there isn't. I'm suspecting that some of you may be seeing where I'm going with this, so I won't ask you to raise your hand necessarily. But ask yourself, before I started talking, whether you really would have endorsed the correct answer, which is that the null hypothesis is the more likely under those circumstances. That is just freaking crazy. Okay? That makes no sense, but it's true. Okay? I will attempt to explain why that's true. And by so doing, explain basically that none of us really understand p-values. Okay, so this comes from Rauder and Morey. The references are at the end of the slide, so you can look it up in your own time if you like. There are graphs and everything. Okay, so if you're not convinced by me, please do go away and work it out as well. I'm going to try and explain to you why, under these circumstances, the null hypothesis is more likely than the experimental hypothesis, which just seems ridiculous. It's because it says at the top, p-values are freaking weird. Okay? We'll start with some non-weird stuff that you probably would assume anyway before I started talking. So, under the assumption the experimental hypothesis is correct, so assuming there is a difference, lower p-values are more likely than higher ones. Yeah? You'd expect that, right? And that's also affected by sample size in the way you'd expect. So as sample size increases, if the experimental hypothesis is correct, then lower p-values are more likely. So as sample size goes up, you'd expect more low p-values. So those things are exactly what you'd expect, right? If there really is a difference, you'd expect low p-values. If you had a bigger sample, you'd expect those p-values to be even lower. So far, that should be, if you've done some stats classes, that should be okay, I hope. The thing that they never tell you in stats class is the next bit, which is if the null hypothesis is correct, then all p-values between 0 and 1 are equally likely. So if there is no difference, you're just as likely to get 0.01 as you are to get 0.99. Okay? Most people do not know that. Most people also do not know that that's unaffected by your sample size. So that's true if you have 100 participants, 1,000, just always true. Basically a problem with the way we do the stats. Because that, for any reasonable measure, that shouldn't be true. So, when you've got a small effect size and a large n, and you're looking over a small range of probabilities, actually it's possible for the null to be more likely than the experimental. Basically, you have to imagine a graph here where the p-values are interacting. Now, as I say, I don't really have time in a talk this short to explain that anymore. I'm happy to talk about it afterwards or show you the graphs, but it is sort of mathematically true and terrible. So, p-values between, these p-values between 0.04 and 0.05, a terrible thing to be pursuing, but we do pursue them. So here's another graph. This is from Mascampio and Lalande. This is looking at the p-values in papers. So on the x-axis, we have p-values going here on this scale from 0.1 down to about 0.02. And on the y-axis, we have how many times they appear in a paper. Now, mathematically, there should be a very simple relationship here, which is that essentially it should be like an accelerating curve. Goes up like this. So imagine sort of that. I should have drawn it on, but sort of an exponential going up like that. If you can imagine that, then what you'll see is that this region here has many more counts than it should. So we have this peculiar prevalence of p-values just below 0.05. Okay? There are really a lot more things between 0.04 and 0.05 than you would expect from any interpretation of the mathematics here. You probably have experienced this yourself. How many times have you reviewed a paper and gone, oh really, p equals 0.045 again? Yeah, okay. You weren't deluding yourself, this is real. These things are much more common than they should be. Why is that happening? Well, there could be lots of reasons. It could be that were all really good at power calculations. And so we're hitting exactly the amount of data we need to collect, and we're behaving optimally, and so they're all about there. Given what I just said about how terrible we are at power calculations, that seems unlikely. It could be publication bias. This is just, if it was 0.06, there's no way you're going to get published. If it's 0.04, you're going to get it published. And maybe you know that, and therefore don't bother submitting it if it's 0.06. It could also be p-hacking, but we'll come back to what that is a bit later. Whatever the reason, it's very important to know that p-values between 0.04 and 0.05, or indeed even between about 0.01 and 0.05, are very weak evidence. Okay, this, if we were going to keep with traditional statistics, the last thing we should use was a criterion of p equals 0.05. Useless, absolutely useless. As you'd expect, there is a relationship between p-value and base factors, so other things being equal, as p-values go down, base factors go up. But base factors are a fairly reliable, trustable measure of how much evidence you have for the experimental hypothesis. P-values, yeah. But anyway, the main point here is that between 0.01 and 0.05, these are all studies, these are real studies in psychology, and we've calculated the p-value and the base factor. Well, I haven't, Betzel's and colleagues have. What you can see is that the vast majority of studies, about 70% of studies, are within the region base factor of 1 to 3. So by the convention here, most studies with a p-value between 0.01 and 0.05 do not have good evidence for there being a difference. The base factor is less than 3. Actually, you can see when you get down to this magic region of 0.04 to 0.05, about here, there's barely any difference. It's about equally likely there is a difference as there isn't. And there's even some studies where actually, if there was anything, there's evidence for the absence of a difference rather than the presence. So whilst p and base factors are related, a p-value between 0.01 and 0.05 is just a really bad criterion. If you're going to, so if you have like, an irrational fear of Bayesian statistics, then that's fine. But for God's sake, lower your p-value. Okay. Yeah, you'll need to lower it quite a lot. There are graphs in Betzel's that will show you how much you need to reduce your p-value if you're going to continue to use traditional statistics. Okay. Good. Right. So, actually, no. I think we're on to that one. Yes. So that actually was my third topic: misunderstanding statistics. What are the reasons that I think we have a replication crisis? We use p-values. No one understands p-values. Okay. Unless there's someone in the audience who hadn't seen that example before and worked out that it was more likely that the null was true. You don't understand what p-value is. And we have this strange prevalence of p-values just below 0.05 for reasons we could discuss. And those values provide only weak evidence. So don't do that. Use base factors. Okay. Another reason for the replication crisis, I think, that's what we're going to call here low reproducibility. So replication is when you run something again and it works again. Reproducibility is the question about whether you actually can functionally run the same thing again. So if you run a different experiment to your colleague and analyse the data in a different way, it's really not that surprising if you get a different answer. So when you're attempting to do a replication, how do you know that you've run the same experiment? How do you know that you've done the same analyses? I think historically we've been quite smug about this and thought, well, if we just read the method and results section, we know what the experiment was and we know what analyses were done. That turns out not to be true. I've had most experience of this in data analysis, but I'm pretty sure it's also true just in getting the methodology right. But to focus on data analysis, my experience, I think, is not untypical. I've requested raw data from other labs several times. First thing to say is that we know that about 70% of requests for raw data after publication end in failure. So even though journals say you have to have your raw data available, when you actually ask for it, you don't get it. On the minority of occasions, and I had that too, but on the minority of occasions where I did get the data, I can only think of one occasion where I managed to replicate the analysis in the paper to get the same results as the paper. This also actually goes for collaborative papers, right? So I've been working with labs around the world, and experiments have been run in different sites, and we wanted to make sure everything's going right. So I try and replicate the analysis done by a colleague, but just using a different stats package. Also, just trying to do it from the description they've given in the paper. I don't get the same results as them. It's happened maybe once. Within the people I work with directly, I think Tina wins the prize of being, yeah, she's in the audience. Tina wins the prize of being the first person I work with where actually the first time I went through her analysis script, I got exactly the same as she did. Which meant, in Tina's case, actually she didn't really need to provide the script. But in most cases, you do. And this, as I say, is not just me. What it comes down to is that actually there's lots of things you do that either aren't fully described in the results section or aren't unambiguously described in the results section. What you need to do is have a proper record of what people do. A journal article is a summary, not a record. How do we solve this problem? Again, it's not difficult, but it does require a change in culture. So what I suggest you do to avoid this problem, besetting the people who come after you, is when your paper has been accepted, at that time, not when someone asks you for it, but at that time, publish your trial level data, so the raw data, as close to raw as you can get. The analysis script, all the commands that get you from your raw data file to the analyses in your paper. Now, you can do this in any stats package. You can do this in SPSS. You have to basically just provide the syntax file. In our lab, we do it in R, and one of the reasons we do it in R, other than the ones I'm going to come to, is that R is really good at pre-processing. So you can actually realistically go from raw data to conclusions, whereas most people who use SPSS actually put their data into Excel and then muck around with it by hand and then load it into SPSS. There's no real good audit trail for that kind of analysis. You can't easily record what you do in a graphic user interface, so it's a really bad way of archiving your analysis. Also, this was about results, but it's equally about the experiments. Consider archiving your stimuli and your experiment code, the code that runs your experiment. Some best practice recommendations, ways to do this. Well, put this stuff in a third-party free repository, something that's always going to be there, can't collapse just because you've retired or your university's gone bankrupt or whatever. Two options. Probably the better known one, Open Science Framework. Thanks to Ben, I'm now aware of something called Zenodo, which actually is, frankly, you're right, Ben, better than OSF in all sorts of ways, and probably is more likely to be here in 20 years than OSF as well. So actually my recommendation would be Zenodo, but you'll hear a lot more about OSF. It's just a data bucket you can throw things in basically, but it's permanent. So that's one thing. Make sure when you're publishing your data you include a code book. That's just a fancy phrase for when you've got a spreadsheet with all your data in and they've got column headings, make sure you explain what each of the column headings mean. Because having received other people's data, I'm doing this for a working memory project at the moment, and you have column headings like SPU 04T9, which I'm sure meant something to the person who coded the data, but is completely incomprehensible to everyone else. That is not publishing your data. To publish it, you've got to be able to communicate. You've got to be able to communicate what it is that you've collected. Also, please use open formats, things like CSV. Don't use SPSS SAB files or Excel files. The reason for that is that those closed formats are complex, prone to error. Excel files have screwed up 1 in 5 experiments in some areas of genomics, for example. But also, you just don't know whether you're going to be able to get that software in 20 years' time. You do know that you'll be able to open a CSV file. Also, for the same sorts of reasons, I would recommend that you use open platforms for your analysis and your experiments. So use things like R and CircuitPy, Python, not SPSS and ePrime. Same sorts of reasons. First of all, because of the nature of this being free and open source software, this will always exist as long as there's one person in the world who cares to keep it going, and the caring is pretty minimal. Things like other projects like this, like C, for example, Linux, lasted for much longer than most things I can think of. No sense of them going anywhere, because you just need one person to care. Whereas things like SPS and ePrime, well, not only are they very expensive, and you need to have them in order to run the experiment, so if you're trying to collaborate with someone in a poorer country, or someone who just doesn't have ePrime, doesn't want to pay £1,000 for it, then they can't use your code. Also, you know, what is the chance that anyone is still going to be running ePrime in 10 years' time? I think basically close to zero. Everyone now seems to hate it. We haven't bought the latest version. It's on 3 now. Exeter hasn't even bought version 2. And once they stop supporting it, you're not going to be able to look at it. Also, in closed formats, you just don't know what's going on inside. You can't see the code. So if there's a bug there, if it's not working right, the only person who can know are the people who own the software, and it's up to them whether they tell you. With open source software, anyone can look at it, and so you will eventually find the error. This happened, for example, in OpenSSL, which is the thing in which all encrypted communications with your bank are based. This piece of software is open source. It's been running for many years. Recently, a bug was discovered in it and fixed. If that had been a proprietary piece of software, there's just, I think, no way that would have happened. Okay. Finally, think about whether you really want to restrict other people's use. We're quite used to putting things in journals with restrictive licenses. Why are we doing that? We're preserving income for multinational publishing companies, and we're making it harder for our colleagues to do research. So when you publish your materials, use free copyleft licenses. So these are licenses that say you can do anything you want with it as long as you share it on the same terms and you attribute it. So for example, CC by SA means Creative Commons by, so attribute to me, and share alike. So if you make a change, you have to share it on the same terms. So you can't take it and turn it into something closed. There are similar licenses for software, which will be most of your analysis code as well. Don't sign over the copyright to the American Psychological Association. Okay, so that's how you deal with low reproducibility. Okay, I'm looking at time. How much longer would you like me to go on for, Ali?
10 minutes.
10 minutes. Okay, fine. We can get through most of these at least. Maybe not them all. We have 3 more. Okay, so another reason I think for the replication crisis, p-hacking. If you've been to my first year lectures, you may remember this. So this is a study conducted with real participants employing legitimate methods and reported truthfully. And here's what it says. We asked 20 University of Pennsylvania undergraduates to listen to either When I'm 64 by the Beatles or Kalimba. Then, in an ostensibly unrelated task, they indicated their birthday, sorry, misspelling there, as month, day and year, and their father's age. We used father's age to control for variation in baseline age across participants. And Ankova revealed our predicted effect. According to their birth dates, people were nearly a year and a half younger after listening to When I'm 64, adjusted mean 20.1 years, than Kalimba, adjusted age 21.5 years. F117, 4.92, P, of course, 0.1. Okay, this is not fraud. This is using legitimate methods, a study that was actually run, but it's obviously impossible. Okay, listening to When I'm 64 does not change the day on which you were born. Okay, hopefully we get that. So how does this happen? How can this possibly happen? It happens from the sorts of things that we all do, or in some cases at least did. I know I did most of these at some point in my career. I've tried to stop doing all of them now. These are things that I think you'll find that a lot of us do. So we might collect quite a lot of dependent variables. We might measure quite a lot of things, but then we'll only report a subset of those. So we might measure 10 or so things, but then only a few of them work, and we'll convince ourselves that's what the study was really about. So we'll just report those. Or we might just report a subset of the experimental conditions that we ran. So, you know, I've got a pre-exposure condition, a no pre-exposure condition, but also an unrelated pre-exposure condition. But that one didn't work very well, so I'm just going to that's between subjects, right? So I can just leave that out. I can just pretend like I didn't done that. That's fine. Or what you can do, which I did at some points in my PhD, I don't mind admitting it, test significance after every 10 subjects. Okay, so run people, see if it's significant, run another 10 people, keep going until it's significant. Yeah, in fact, one piece of advice I received was, let's run another 10 participants. If the p-value improves, that's great. If not, we'll just act like we didn't test those last 10 people. I won't attribute that. Also, when you've got a lot of dependent variables, you've got a lot of flexibility for putting covariates into your analysis to correct for various things. Okay, whole other talk. You can't correct for differences. That's not how it works, right? If you want to control for something, you have to run an experiment. You can't just put it as a value into a stats and hope that it magically fixes your design. It's fantasy. Anyway, if you do all of those things, then this really great paper, which is the Simmons one that I got the quote from, you end up with a false positive rate of about 60%. So false positive means you report a significant difference when there's nothing really there. And they can show this through simulation studies. So if you do those 4 things in a study, there's about a 60% chance that the significant results you're reporting aren't real. Okay? So more likely than not, they're not real. That seems to be a pretty good reason for us being in a replication crisis. How do we solve this problem? I refer you back to everyone's favourite bongo playing, atom bomb designing Nobel laureate, Richard Feynman. He said this at a commencement address in the 70s. The first principle is that you must not fool yourself, and you are the easiest person to fool. So you have to be very careful about that. After you've not fooled yourself, it's easy to not fool other scientists. You just have to be honest in the conventional way after that. And I think that represents most of what we've got here. Yes, there are some evil people who are actually trying to fool us, but I don't believe that of most of my colleagues. Mostly we're fooling ourselves, and then we're communicating our genuinely held belief of a falsehood to other people. How do you avoid fooling yourself and therefore avoid fooling others? Well, first thing to say is, and not everyone will agree with this, but this is opinionated, so I'm going to say it. Start by getting your procedures right, particularly if you're doing lab-based work where it's meaningful to test. Say you test a few people and you find that none of them can do it at all. That actually is useful information, even if it's not publishable. You tweak it and you try again. Get your procedures right until you're really happy with that this is the best version of the experiment you can run. And fine, do that with small samples if you like, who cares? When you're happy that that's the best version of the experiment, then get a bit of paper, write down what your hypotheses are, what your design is, what the independent and dependent variable are, what your intended sample size is, do a power calculation to work out how much you should be testing, write down your analysis plan. So what stats are you going to do? Are you going to exclude anyone? What analysis techniques are you going to use? Then consider getting it, well, the old-fashioned phrase is notarized. In other words, get that statement ticked off, rubber stamped by some other system that means there is no doubt that you did it on a particular date. That's, I think, for me, and again, opinions differ, that is a way of just keeping yourself honest. Yeah? I don't think doing that to try and ensure that people aren't fraudulent is going to work, but I think it might, if you find that's helpful, if you find the sort of person who finds like setting goals and then telling other people about them so you feel bad if you don't meet them, then notarizing is good. The modern phrase for this is pre-registration. So what you can do is you can go to a website, when you've got this information, you can type it into a web page and press a button, and that gets marked as having been logged by you on a particular date. And depending on the website, you can make sure that's not visible to anyone else until you choose to release it. But they work in different ways. Do that and then follow your plan. That way, it's clear that your analysis and your plan, what you decided to do, was agreed and decided before you collected the data. So you can't possibly have done all this sort of like we're trying everything until something works, because you said before you collected the data what it is you were going to do. Now follow the plan. You can't lose here really. Either it is what you predicted, in which case you say so, or it isn't what you predicted, in which case you say so. Those are both pieces of information. But what it does do is just make it much harder for you to collect data and then construct an entirely artificial narrative backwards from what you found. Okay, what we got, about 4 minutes?
Yes.
Okay, right, so speeding up a little bit then. Another thing that I think has been a cause of the replication crisis is basically poor project management. Questions that you might ask yourself. Think about a particular topic in your field. Think about redundancy effect. Some of you will be able to answer this question, others won't. How many experiments have I run on this topic in my career? How many of them worked? How did they differ from each other? When looking at my hard drive, which version of this file is the experiment I actually ran, rather than the pilot version of the experimental program? Which of these is the complete and correct data set? Which is the analysis the reviewers want me to redo? I've struggled with that for most of my career and had minor panic attacks every time a paper came back from review, going, oh shit, I can't get the thing that I put in the paper, let alone get it fixed. I can't get the thing I originally reported. And generally I can get there in the end, but it's just a nightmare. But it's not just for managing yourself. Who's experienced this? This is for the people who have people who work with them. So you have an experiment or analysis that was done by a project student, a PhD student, a postdoc, a colleague, and then panic, I don't have the files. They had the files and they've left. Or I do have the files, but they make no sense. I've definitely had that experience. How do you solve this problem? You use a version control system. Okay, you may not have heard of this term. It's like a shared folder, like a OneDrive folder, but it's a lot better. In a version control system, you don't change the file names. So it's the last time you ever have to write analysis final, really final, honest, new as the name of the file. Okay, you just save your new analysis over the old one with the same file name, and you commit it, which means record it with a message that has the time that you did it. This is it's timed automatically. A quick message saying updated to solve this problem. Whatever. You can't lose anything unless the whole system collapses, but you can always go back. You can always go back to a previous version. And you have a perfect audit trail. You can see every change that you made and when it happened. So the question of, which version is the one that I ran the experiment on? Well, you know, because you know when you collected the data, because that's in the archive. So you know the version that was there immediately before you collected the data is the one that you ran. It can do much more than that. Things that I think in time I won't go over, but it allows for very flexible working practices like branching and merging that allows different people to work on the same project at the same time without getting in each other's way. It allows you to do code review, which is something I recommend that you all do. Don't think of yourself as a solo researcher. Team up, at least pair up. Okay, at some point before you publish the paper, please let someone else have a look at your analysis script and check that they're happy with it too, someone you're working with. Version control systems make this very easy to do. Okay, so how to do it? Pick a version control system. My recommendation, pick a one that's based on something called Git or SVN. Doesn't really matter if you don't know what those are at the moment. They're the most powerful modern versions. They both work with R. You can get them in various places. GitHub is probably the most famous one. GitLab is an alternative. As we have our data protection officer in the room, I should say that bear in mind that you shouldn't be putting sensitive or confidential information into these cloud-based systems. Anonymize your data before upload. Never store de-anonymizing information in it, and make it private to your team unless you want to make it public. This is essentially a problem with doing anything other than keeping files on your encrypted drive on your personal machine that's locked in a room. Okay, but as soon as you go beyond that, there's a potential that it'll get hacked, and you need to protect against that. Plymouth's OneDrive is also a cloud-based system. If you didn't know, it's based in Eastern Europe, run by a very big software company. Seems to me to be quite a big target. I don't think it's ultimately that much more likely that OneDrive gets hacked or GitHub gets hacked. What does matter, of course, is that if Plymouth OneDrive gets hacked, then the IT guys here get in trouble, and if GitLab gets hacked and you're on it, then you get in trouble. So be smart. Don't put anything sensitive in these things. Okay. I think I'll skip over the last point, which was the most controversial one. Anyway, so I can cut myself a bit of slack. Okay, so here's what you can do today to try to help solve the replication crisis. Start doing power calculations. Many of you are not collecting enough data to actually make a reasonable conclusion. Start using Bayes factors. Then if your experiment doesn't work, you can actually publish it, yeah? As long as you've got good evidence for the null. Start using open platforms like R and Python rather than SPSS and E prime. Start using version control, things like GitHub. Consider pre-registering your next big study. Something like aspredicted.org does this very efficiently. It take, I think, less than an hour in most cases. Publish your data analyses on something like Zenodo or Open Science Framework. The last one I didn't have time to cover, but basically the final reason I was going to go on to was another reason for the replication crisis, I think, is that we have this pressure to publish a large number of papers that we didn't have time to talk about today. So thank you very much.
Thank you, Andy. Any questions?
Oh, there was one here first.
Yeah, I just feel quite mildly irritated that we just spent a long time learning about SPSS and all those statistics that you've just now kind of demolished, really.
Sorry.
And is the department going to change this?
Already is.
Right.
Yeah. So the first year, the new curriculum for undergraduates is all based on R.
Right.
Yeah. The master's
Why
course.
are we on the conversion course doing all this old stuff now?
Because it's not possible to change everything instantly. So what we're doing is we're bringing in.
No one's mentioned it, and this is not a compulsory lecture. Do you know what I mean?
Yeah, yeah. Well, I mean, this is obviously a question that probably you need to address to the people who are designing your course. But to answer it briefly, the conversion course is based on taking bits from the undergraduate program. And the undergraduate program is at the beginning of a 3-year process to update its syllabus. We're doing it as the students go through. So we've updated the first year this year. Next year, those first years will become second years, so both the first and the second year will be updated from the third year. Your conversion course doesn't pull anything from the first year course, so it's not pulling anything from the curriculum. So that's the answer.
Well, actually, I was hoping that you would say more about the last point.
Yeah.
Because I think that the incentive structure at the institutional level is probably one of the strongest forces that have been causing this problem.
Shall I do that then? Is that all right? I'll do this. I'll do a 2-minute answer.
Seminar.
Do another seminar. Okay. Now this will be quick because this is now an answer to your question, Giorgio. Okay. So, as Giorgio was saying, I think there's substantial pressure on the number of publications that you make. So these are from my own career. So when I was looking for my first postdoc position in the late 90s, I was told that successful applicants for this junior postdoc, so straight out of PhD, typically have 4 first author publications. I was appointed here as a professor in 2012. Thank you very much. The head of school at the time, Simon Handley, had a little chat with me when he offered me the job and said, not everyone wanted to offer you the job, but I thought it was a good idea. I said, okay, well that's fine. So there's this view expressed that a professor should have at least 50 publications. I didn't have anything like 50 publications at the time. I had about less than 30. a lot of us go through PDR. PDR, for those who don't know, is your annual appraisal for academics. How many people have written something like this in their PDR at some point? Yeah? Okay, I'm going to publish 2 papers this year. This year. Submit. Well, yes, submit. I will submit 2 papers this year. Yeah. How many people have gone to a talk? Been some here recently, not under Ali's tutelage, I think, but a little longer ago, where the first thing you say to introduce the speaker is, Professor Esteem has published over 200 papers, and this is meant to be something that you're impressed with. Okay. I think probably this pressure to publish increases the non-replication rate. People are rushing things out before they're ready, they're piecemeal publishing. I think those of us who feel the pressure enough might do things that are actually unethical in order to meet criteria that means that they get a job. What's the answer? Well, the answer is, start focusing a bit more on quality over quantity. Those of you that, again, are on the staff side, you know that parts of our environment already do this. So Ref 2021, this department will get a perfect score on the Ref if we all published 1 4-star paper every 3 years and nothing else. Okay, so great paper in 2018, nothing in 2020, 2019, nothing in 2020, great paper in 2021. We all did that, we would have a ref return that was twice as good as Oxford's. Okay. So, there's already that thing. Part of our environment says focus on quality rather than quantity. I think if we did that as well, it would have some other benefits. As reviewers, as you spend more time in academia, you get more papers to review. I think if we were publishing less, we could spend more time reviewing each paper, which would be better quality control. We also, as authors, spend less time formatting questions in Word. Don't do that, by the way, don't use Word, but that's another talk. Arguing with reviewers about points of detail, mainly because we don't really want to run on a study because then we won't get it in, we won't publish it in time for our next PDR meeting. Also, it reduces the amount of money that we end up giving to publishing companies and professional societies to make them rich. So if you're publishing an article, open access, it costs about £1,500 per article. In case you're thinking, God, that's ridiculous, which it is, by the way, it is ridiculous. But it's much lower than this university is paying for you to publish if you're publishing in subscription journals. The subscription journals are really expensive and lots of libraries buy them. So when you estimate how much publishing the subscription journal costs the academic community, it's about £4,000 per paper. So you just publish a paper in, I don't know, QJP, under the subscription model, it just costs the academic community globally £4,000 for you to do that. Okay. So, all good reasons to publish fewer, better papers. Now, so that's a good idea for everyone, apart from anyone who wants a job or wants to get promoted. And this is really useful. If you're thinking about making a promotion application, I have no idea how promotion works in this university, but there is data on this from psychology. H-index, which if you don't know, probably don't have the time to explain, but basically it's a measure of okay, so H is, if you've got H8, that means you've got 8 papers, each of which have been cited at least 8 times. An H of 8 is at the 40th percentile for a professor in psychology, a bit below average, but it's quite high for an associate professor, about 80th percentile. So there's a sort of a tipping point around rate H equals 8 on, not on Google Scholar, but on meaner versions like ISI. And so if you're using H-index as one of your decision-making criteria in promotion or appointment, then you might use 8 as a number. But think about what that means if you're following this strategy of maximum quality. The thing that would maximise research output as measured by the graph in this department, you publish 1 4-star paper every 3 years and nothing else. On that basis, it would take you over 22 years to get an H-index of 8. Okay, which may be fine. You know, if you think you can publish a 4-star paper out of your PhD and you get your PhD at 25, then you only have to be 47 to become a pro. But actually, in reality, That's not. That's the quickest you could do it, right? Or if you were like me, told that really professors should have 50 papers, then it's going to take you 150 years to become a professor. So start getting the cryogenics sorted out, right? Okay. So yeah, that's my answer.
Anything else that may not require such a...
Well, I'm out of slides, so it's not gonna...
Would you make your slides available to us?
Yes, of course. Yeah, and in fact, all materials for this presentation are available in a free software license. Actually getting them to you, that might take a day or so. I'm recording the audio. We're going to see whether Ponoptos work. But yes, they'll be public available.
Thank you.
Yeah, Caroline.
Can you calculate B values for any kind of statistics? Like you...
That would brilliant. You have that p-value for anything, right?
Yes, so it's the same with B, I mean...
Oh, you mean base values?
Yes, base
Yes,
values.
yeah. For anything you can do with traditional statistics, there is a Bayesian way of doing it. Yeah, so I picked on t-tests because everyone knows what they are, but actually you can do all sorts of things with Bayesian statistics that are very hard to do with traditional statistics. So I think you had an interest at one point in mixed models. Yeah, so the natural progression of mixed models is hierarchical Bayesian analysis, which is just a much better way of dealing with the fact that you have structure both at an individual and a group level. So yeah, we're not covering that in the undergraduate course. Do you cover any of that? Is Ben gone? Oh, yeah, okay. I'm not sure what Ben covers in the other course, but yes, answer is Ed.
Teach students how to do it right. How do they do practical research exercise as part of an undergraduate degree when you need 60 people on each or
Right. Okay. So the question basically is having a sufficiently powered study achievable in the context of a class? And of course, it depends on the class and what you do. It might not always be achievable. There are many things that we do for teaching where we have to be clear that this is being done for teaching purposes, and in the following ways, this is not how you should really do it. So you can say that. Another thing you can do is, it depends what you're teaching, right? So if you're teaching statistics, which is the thing I've thought about most so far, then of course it's not beholden on you to get the students to collect those data. You just need large data sets. So if you're teaching statistics, you just make sure they have access to large realistic data sets, which is what I've tried to do in the first few courses. If you're getting them to collect the data, then yeah, that's an issue. We did that in 411. How many people do they test, Peter, roughly?
Like 30 for each group or something.
Okay.
I think a research project.
Yeah, master's project.
Yeah.
If you have 40 points and 120 pounds, what am I going to do with that? I'm just faced with that problem. I can max test 40 people. I already know that really this is not a large enough sample size. We just talked about it this morning. But I can't physically get more people unless I get volunteers,
Yeah.
which I did actually for my undergrad project.
Well, maybe that's fine, right? In the sense that it's fine of what the reason for doing a project is to gain a series of skills which you can still apply, irrespective of the amount of data you've collected. What you haven't got is a data set that's publishable.
But that's frustrating. I have a really good project, for example, and I think this is worth publishing, but you're telling me about actually this is just a bit of kindergarten show that you're doing here because you won't ever have the figures to publish it. But I feel betrayed for my career path here. You just walked it out for me.
Okay, so here you go. So, yeah.
Points administrator.
Yeah.
Chip in here. Because and I've had to reassure even undergraduates doing their projects about this, that we do not mark a project by sample size, and that, as you say, it's a teaching exercise, and so they shouldn't get hung up on the fact that they've got an undergrad study and they're likely to get, even with P statistics, a null result, and so on, and that we're marking for the assessment purposes the quality of the exercise, as it were, rather than the power of the.
That's right. Well, I do have some other, yeah, okay.
And that's for the undergrad. we can get over that with the undergraduates by getting students to pair up or going in threes so that they can collect a reasonable sample when they pull their points, etc. And I think it's a valid thing to do in the context of scientific practice. We all collaborate. Few
Yeah.
of us do studies on our own anyway. The master's students, though, it is more of a problem because they have much more ambitious goals. They've already done one project usually, and they're trying to do something much more. And they tend not to be pairable, upable, and they want to do things on their own, and they're therefore much more restricted in the sample size.
Okay.
And it does link into publication. A lot of them want to get onto PhD courses and so on and do things like that. So there is a problem.
Well, no, there is a problem.
To sort of
Yeah.
pacify them. With
Okay, John, so there is a problem in the same sense that there's a problem that diamond is hard. Right? I mean, we can't make this problem go away just by pretending it isn't there. There are a number of things I think we can do. One of them is, yes, at the moment it seems to be the culture that master's students work entirely individually. That's the culture in psychology, right? I have friends who do PhDs in other subjects who have never worked on their own on anything. You know, I have a friend who works at CERN, okay? His PhD was part of the work of CERN, yeah? He could not have done that on his own. He could not have gone to the research committee and go, I want to put a 22-mile ring under the floor and run my own particle acceleration. So, to the extent that what we're asking students to do doesn't generate meaningful data, we need to ask them to do different.
And I agree, the course is all set up about they've got to design, they've got to write protocols, they've got to, we're forcing them to do that individually, and it doesn't fit some.
Yeah.
I don't think that's really true. I think we've had many instances of years where students have worked in practice projects on the master's course. And actually,
I think it's very rare, and we should encourage it.
yeah, but I think it's
No, it does.
But I think the other thing is we've talked about it already today that actually there are designs that you can do that are powered with better people, and we should be doing those more often.
Another way of activating a focus on an explicit acknowledgement of the limitations, of the project, and making that awareness of the need for that in individual research projects clear to students. I think as they
Yeah, you're right. We said that in
familiar
that,
with these caveats.
So we said that, and that is one solution. Basically, this is a teaching exercise solution. What I'm hearing is that's not an ideal answer. I think what Ben's saying is a better solution, which is if you want to do something that's publishable in that amount of time and you want to do it on your own, then make sure you're doing something where you can find an effect with the resources that you have. So let's start off with never run a between subjects design, okay? Because you will never have enough people for that to work. Do it within subjects. That's number one. That will help a lot. Power is often fine at 30 participants if you've got a within subjects design. Two, look at something where you expect the effect size to be large. Yeah? Median effect size is 0.5, but there's a range. There are plenty of effects in psychology where the effect size is greater than 1. Okay? You do not need large samples to competently detect. I mean, there are other representative issues, right? Because a small sample can always be less representative of the population. But in terms of pure power calculations, if you're picking within subject designs with large expected effect sizes, then you can totally do it. Pick things where there isn't much individual variation. It's like a physics is an obvious example. Or things where you're collecting a lot of data per person, and so what you're doing is you're making a conclusion about individuals.